Hello! Today we're going to dive into two of the most fascinating and fundamental concepts in quantum physics. By the end of this video, you will be able to explain the physical intuition behind the Heisenberg uncertainty principle and understand how it arises from the wave nature of particles. You will also be able to explain how confining a particle leads to quantized energy levels, and you'll be able to calculate these energy levels for a simple system. These ideas are at the heart of how the universe works at its smallest scales, and they are essential for understanding everything from the structure of atoms to the behavior of semiconductors. Let's begin with our first topic, the Heisenberg uncertainty principle. This principle, formulated by Werner Heisenberg, is one of the most famous and often misunderstood ideas in quantum mechanics. At its core, it tells us that there are fundamental limits to how precisely we can know certain pairs of properties of a particle at the same time. It's not a limitation of our measuring devices. It's a fundamental property of nature itself. The most common form of the principle relates a particle's position, which we'll call delta x, and its momentum, which we'll call delta p. Here, delta x represents the uncertainty in the particle's position, and delta p represents the uncertainty in its momentum. The symbol T, pronounced h bar, is a fundamental constant of nature called the reduced Planck constant. It's a very, very small number. The inequality tells us that the product of these two uncertainties must always be greater than or equal to c over 2. This means you can't make both uncertainties arbitrarily small. If you try to measure a particle's position with extreme precision, making delta x very small, the uncertainty in its momentum, delta p, must become very large, and vice versa. So where does this strange principle come from? The answer lies in the wave-particle duality of matter. In quantum mechanics, particles like electrons and photons don't just behave like tiny balls, they also behave like waves. This is a crucial concept. Every particle has an associated wave, and the properties of that wave determine the particle's behavior. The wavelength of this matter wave, denoted by lambda, is inversely proportional to the particle's momentum, p. This is given by the de Broglie relation, lambda equals h over p, where h is Planck's constant. Now, let's think about what it means to have a well-defined position versus a well-defined momentum. Imagine a wave that is spread out over a very large region of space. This wave has a very precise single wavelength. Because wavelength is directly related to momentum, this wave represents a particle with a very well-defined momentum. However, because the wave is spread out, we have no idea where the particle is. The uncertainty in its position, delta x, is very large. Now what if we want to know the particle's position very precisely? To do that, we need a wave that is localized to a very small region of space. But how do you create a localized wave? You have to add together many different waves with different wavelengths. This combination of waves is called a wave packet. Because this wave packet is made of many waves with different wavelengths, it doesn't have a single, well-defined wavelength. And since momentum is tied to wavelength, the particle it represents doesn't have a single, well-defined momentum. The uncertainty in its momentum, delta p, is very large. So you see, there's a fundamental trade-off. A wave cannot be both perfectly localized in space and have a perfectly single wavelength. This inherent property of waves is the physical origin of the Heisenberg uncertainty principle. Let's look at a quick example to see how this works in practice. We'll calculate the minimum uncertainty in the position of an electron. Let's say we have an electron, which has a mass of about 9.11 times 10 to the negative 31 kilograms. We measure its speed to be 500 meters per second, but our measurement has an uncertainty of 0.003%. Our goal is to find the minimum uncertainty in the electron's position. First, we need to find the uncertainty in the electron's momentum, delta page. Momentum is mass times velocity, so the uncertainty in momentum is mass times the uncertainty in velocity. The uncertainty in velocity, delta v, is 0.003% of 500 meters per second, which is 0.015 meters per second. Now we can calculate the uncertainty in momentum. Delta p equals the mass of the electron times delta v, which is 9.11 times 10 to the negative 31 kilograms times 0.015 meters per second. This gives us an uncertainty in momentum of 1.3665 times 10 to the negative 32 kilogram meters per second. Now we can use the uncertainty principle to find the minimum uncertainty in position. The principle states that delta x times delta p is greater than or equal to h bar over 2. To find the minimum uncertainty in position, we'll use the equality. We know h bar is approximately 1.055 times 10 to the negative 34 joule seconds. Plugging in our values, we get delta x equals 1.055 times 10 to the negative 34, divided by 2 times 1.366, 5 times 10 to the negative 32. This calculation gives us a minimum uncertainty in position of about 3.86 times 10 to the negative 3 meters, or 3.86 millimeters. So, even with a very precise speed measurement, the fundamental wave nature of the electron means we can't know its position any better than a few millimeters. This is a direct consequence of the uncertainty principle. Now, let's move on to our second major topic, particle confinement and energy quantization. This idea explains why atoms have discrete energy levels and why lasers work. It's a cornerstone of quantum mechanics. In the classical world, if you have a ball bouncing in a box, it can have any energy you want. You can throw it a little harder or a little softer, and its energy will change smoothly. But in the quantum world, if you confine a particle to a small space, its energy can no longer be continuous. It can only take on specific, discrete values. We say its energy is quantized. This is like a staircase, where you can only stand on the steps, not in between them. The particle can only exist in these specific energy states. Why does this happen? The answer, again, comes from the wave nature of particles. When you confine a particle, you are essentially confining its associated wave. Think of a guitar string. When you pluck it, it vibrates, but only certain vibrations are allowed. The ends of the string are fixed, so the wave must have zero amplitude at those points. This means only waves that fit perfectly into the length of the string are allowed. These are called standing waves. A quantum particle in a box behaves in a very similar way. Its wave function, which describes the probability of finding the particle, must be zero at the walls of the box. This boundary condition forces the wave to form standing waves, just like the guitar string. And because only certain standing waves are allowed, only certain wavelengths are allowed, and since energy is related to wavelength, only certain energies are allowed. This is the physical intuition behind energy quantization. To make this more concrete, let's analyze a simple model called the particle in a one-dimensional box. Imagine a particle of mass m trapped in a box of length L. The walls of the box are infinitely high, meaning the particle can never escape. Inside the box, the particle is free to move, so its potential energy is zero. The behavior of this particle is described by the Schrödinger equation, which is the fundamental equation of quantum mechanics. For this simple case, the equation is negative h bar squared over 2 meters times the second derivative of the wave function psi with respect to x equals the energy E times the wave function psi. The solutions to this equation, psi, are the wave functions, and the corresponding values of E are the allowed energy levels. The boundary conditions are crucial. Because the walls are infinitely high, the particle cannot exist outside the box. This means the probability of finding the particle at the walls must be zero. Therefore, the wave function psi must be zero at x equals 0 and x equals L. So we have two conditions, psi of 0 equals 0 and psi of L equals 0. The general solution to the Schrödinger equation for this problem is a combination of sine and cosine functions. But when we apply the boundary conditions, we find that only sine functions work. The solution that satisfies both boundary conditions is psi of x equals a times sine of kx, where k is a constant. The first boundary condition, psi of 0 equals 0, is automatically satisfied because sine of 0 is 0. The second boundary condition, psi of L equals 0, is the one that quantizes the energy. For psi of L to be 0, the argument of the sine function, k fel L, must be an integer multiple of pi. So, k fel L must equal n times pi, where n is an integer. Notice that n cannot be 0. If n were 0, k would be 0, and the wave function would be 0 everywhere, meaning there's no particle in the box. So the lowest possible value for n is 1. Now that we have the allowed values for k ray, we can find the allowed energy levels. From the Schrödinger equation, we can see that the energy E is equal to h bar squared k squared over 2 meters. We just found that K must be N times pi over L. Substituting this expression for K into our energy equation, we get E equals h bar squared times the quantity N pi over L squared, all divided by 2 meters. Simplifying this, we arrive at the famous formula for the quantized energy levels of a particle in a box. E sub n equals n squared times pi squared h bar squared, all divided by 2 milliliters squared. This is a profound result. The energy of the particle is not continuous. It can only take on these specific values, which are determined by the integer n, the size of the box L, and the mass of the particle m. The integer n is called the principal quantum number. Each value of n corresponds to a different energy level and a different wave function. Let's look at the first few energy levels. For n equals 1, we have the ground state energy, E1. For n equals 2, we have the first excited state, E2, which is 4 times E1. For n equals 3, we have the second excited state, E3, which is 9 times E1. The energy levels are not evenly spaced. They get further apart as n increases. This quantization of energy is a direct consequence of the wave nature of the particle and the boundary conditions imposed by the box. It's a fundamental prediction of quantum mechanics. Let's work through an example to calculate the ground state energy of an electron in a one-dimensional box. Suppose we have an electron confined to a box of length 0.1 nanometers. This is a typical size for an atom. We want to find the energy of the lowest possible state, the ground state. For the ground state, the quantum number n is 1, so we'll use our energy formula with n equals 1. The formula for the ground state energy is E1 equals pi squared h bar squared over 2 milliliters squared. Now we just need to plug in the values for the constants and the given length. We have pi squared times h bar squared, which is 1.055 times 10 to the negative 34 squared, divided by 2 times the mass of the electron times the length of the box squared, which is 1.0 times 10 to the negative 10 squared. Let's calculate the numerator and the denominator separately to avoid errors. The numerator is pi squared times h bar squared, which is approximately 1.096 times 10 to the negative 67. The denominator is 2 times the mass times the length squared, which is approximately 1.82, 2 times 10 to the negative 50. Now we divide the numerator by the denominator. This gives us a ground state energy of approximately 6.015 times 10 to the negative 18 joules. This is a very small number in joules, so it's common to express it in electron volts. 1 electron volt is about 1.6 times 10 to the negative 19 joules. Dividing our energy in joules by the conversion factor, we find that the ground state energy is approximately 37.6 electron volts. This is a significant amount of energy, much larger than the thermal energy at room temperature, which is why we don't see these quantum effects in our everyday lives. Let's quickly recap what we've learned today. We started with the Heisenberg uncertainty principle, which states that there's a fundamental limit to how precisely we can know a particle's position and momentum simultaneously. This principle arises directly from the wave nature of matter. Then, we explored how confining a particle to a small space, like a box, leads to energy quantization. The particle's wave function must form standing waves, which restricts its energy to specific, discrete values. We derived the formula for these energy levels and calculated the ground state energy for an electron in a box. These two concepts, the uncertainty principle and energy quantization, are not just abstract ideas. They are the foundation for understanding the behavior of atoms, molecules, and materials, and they have led to countless technological innovations, from transistors to lasers. I hope this video has given you a clearer and more intuitive understanding of these powerful ideas. Thank you for watching.